In this video, we will be solving sums from exercise 9.3 of Maharashtra Government Textbook Maths Part 1 11th Standard. The sums are based on probability, and yeah, with that, let's begin with our questions. So if you check the first question, it says that a bag contains 3 marbles, I'm sorry, 3 red and 4 blue marbles. 2 marbles are drawn at random without replacement. If the first marble is a red marble, then what is the probability that the second marble is a blue marble? See, if you have already taken out a red marble, then out of, sorry, not 4, 3 red. Out of 3 red, you are left with only 2 red marbles in the box, and there are 4 blue marbles. So given that the first marble is a red marble, the probability of the second marble being a blue marble, probability of blue, given that the first marble was a red marble, this probability is going to be, like we said, 4 blue marbles, and there are just 2 red marbles, so total there are 6 red marbles, so the probability will be 2 by 3. Okay, going ahead with the next question. A pencil box contains 5 green pencils and 7 yellow pencils. 2 pencils are chosen at random from the box without replacement. What is the probability that both of them are yellow? So if you're selecting 2 pencils, then the total number of possibilities that you can have, the total number of selections, the total number of selections are going to be how many? 5 and 7, 12 pencils. So 12C2 is the total number of possibilities. We want both of them to be yellow pencils. So any 2 out of the 7 yellow pencils can be selected in 7C2 ways. So yeah, 7C2 upon 12C2 is the required probability. You can calculate it by 7 into 6 upon 2 into 1 divided by 12 into 11 upon 2 into 1. That 2 into 1 in the denominator gets cancelled, and you are left with 7 into 6 upon 12 into 11. 6 cancels off 12, and the final answer there will be 7 upon 22. Going ahead with question number 3. In a sample of 40 vehicles, 18 are red, 6 are trucks, okay, out of which 2 of them are red. Suppose that a randomly selected vehicle is red. What is the probability it is a truck? Okay, let's process that again. In a sample of 48 vehicles, 18 are red. Okay, so there are 40 vehicles, out of which 18 are red and 22 are not red. And 18 are red, 6 of them are trucks. Okay, there are 6 trucks, out of which 2 are red, and the other 34 are cars. Okay, and suppose that a randomly selected vehicle is red. Okay, so probability of the vehicle being a truck is what they are asking us. Okay, so probability of the vehicle being a truck, given that it is a red vehicle. So this is a question on conditional probability, and we write the solution in this manner. We say this will be P of T intersection R divided by P of R. So P of T intersection R means it's the probability of getting a red truck. Probability of getting a red truck. See, there are only 2 red trucks that are available, and 2 red trucks out of 40. The probability for that will be 2 by 40 divided by probability of getting a red vehicle. So there are 18 red vehicles out of 40. So probability of getting a red vehicle would be 18 by 40. That 40 gets cancelled, and 2 upon 18 will make it 1 by 9. That's the final answer for question number 3. Yeah, so this was a sum based on the conditional probability concept. For all those who don't know that concept, I'll just explain it, and for all those who know it, you can just fast forward the video and continue with the next question. So the conditional probability concept goes something like this. Say for example, if I have a set A, and let us say the set A is 1, 2, 3, 4, and let us say I have a set B also. The set B is 3, 4, 5, 6, 7, 8. So A union B, if I consider the total numbers that I have numbers ranging from 1 up to 8, and I am randomly selecting a number. If I randomly select a number and it just happens out to be a number from the set B, I am not disclosing which number it is, but I am only telling you that it is a number from the set B. So let us assume that event B has already occurred. Event B has occurred. Now I have not disclosed the number. Okay, if I tell you that event B has already occurred, then now what is the probability that event A might have occurred? So you know that if event B has occurred, there are how many? 1, 2, 3, 4, 5, 6. There are 6 possibilities if I say that the event B has occurred, and If event B has occurred, then the only possibility by which event A might have occurred is the number which has turned up should either be 3 or it should be 4. If it is 3 or 4, then only we can say that event A has occurred. So what is the conditional probability that event A has occurred given that event B has occurred? Okay, so given that event B has occurred, A can occur only in two possible ways. So we will say probability that event A will occur given that B has occurred will be 2 divided by the total number of possibilities are not 1 to 8 now. Because I've said that B has occurred, the total number of possibilities are only 6. So the denominator will be 6. And that is finally 1 upon 3. Now we don't need that 1 upon 3. We are basically interested in the concept. So how did you get that 2? See, that 2 basically represented those elements of A which were available in the event which has already occurred. That is elements of A which were there in B. Elements of A which are there in B, it is actually represented by A intersection B. So this is P of A intersection B, or 2 would specifically represent N of A intersection B divided by that 6. That 6 was not N of S. Sample space would contain all numbers from 1 to 8, but denominator was not N of S, it was N of B, number of elements that were present in B. So in the denominator we will have N of B. Now if you want, you can divide the numerator and denominator with N of S. So we have N of A intersection B upon N of S divided by N of B divided by N of S. The numerator would represent probability of A intersection B, and the denominator would, in case if I've said the denominator, I meant the numerator represents P of A intersection B and the denominator represents N of P of B. Okay, so N of B upon N of S being P of B, and yeah, that's how you arrive at the formula. P of A intersection B is P of A intersection B upon P of B, and that's the very formula I have used for solving this question number 3. Okay, so if that's clear to all of you, we can go ahead with question number 4. If not, just rewind the video once and watch that entire explanation again. It will help you in understanding this third sum in a better way. Going ahead with the fourth one. The fourth one says, from a well shuffled pack of cards, 2 cards are drawn at random. Find the probability that both are diamond cards when the first card drawn is kept aside. So if you're drawing one card and just keeping it aside, that means you are drawing the cards without replacement. Okay, so how many diamond cards are available in a pack of 52 cards? 13. Okay, so we need 2 diamond cards and they can be selected in 13 C2 ways, divided by how many cards you are selecting. You're selecting 2 cards out of 52, and 2 out of 52 cards can be selected in 52 C2 ways. Just to evaluate it, you can just say 13 into 12 upon 2 into 1 divided by 52 into 51 divided by 2 into 1. That 2 into 1 gets cancelled in the numerator and denominator. The leftover numbers are 15, 12, 13 and 51. So 4 cancels off 12, 4 into 3 will be 12 and 4 into 13 will be 52. 3 ones are 3, 3 17s are 51. So I'm sorry, 4 13s are 52. So 13 and 13 also get cancelled, and the final probability for that fourth question is 1 upon 17. That's how we are answering the fourth question, and with that we go ahead with our next question. That's number 5. Yeah, number 5 is right here. So ABC try to hit a target simultaneously, but they are hitting it independently. Their respective probabilities of hitting the target are 3 by 4, 1 by 2 and 5 by 8. Find the probability that the target is hit exactly by one of them. So exactly by one of them means P of A intersection B complement intersection C complement plus P of A complement intersection B intersection C complement plus P of A complement intersection B complement intersection C. Okay, so if they are hitting it independently, the intersection is the same as multiplication. It is yet another inference of the independent events concept, or the conditional theorem that we have just learned. It's an inference of the conditional probability concept only. I will discuss it at the end of this sum. Till then, let's just continue with this. P of A intersection B complement intersection C complement. Because they are independent, you can write it as P of A into P of B complement into P of C complement plus the other two terms also in a similar way. Evaluating it, we are going to have P of A, probability of A hitting the target being 3 by 4 into keep in mind we want B complement. So if the probability of B hitting the target is 1 by 2, probability of B not hitting the target is 1 minus 1 by 2, which is 1 by 2 only, into P of C complement. So 5 by 8 is the probability of hitting, 3 by 8 will be the probability of not hitting, plus the next one is P of A complement into P of B into P of C complement. The numbers will be 1 by 4, 1 by 2 and 3 upon 8, plus the last one is P of A complement, B complement and C. So that will be 1 by 4, 1 by 2 and C, the probability of C hitting is 5 upon 8. Okay. So evaluating that full thing, we have 3 into 1 into 3, which is 9, plus 1 into 1 into 3, which is 3, plus 1 into 1 into 5, which is equal to 5. The whole thing divided by 4 into 2 into 8, which is equal to 64. So in the numerator, what we have is 17 and the denominator is 64. That's how we are answering your A part. And yeah, with that we go ahead with answering the B part as well. The B part says the probability that target is not hit by any one of them. So target is not hit by any one of them means probability of A complement, intersection B complement, intersection C complement. Now that these are independent events, we know that we can multiply the probabilities, like P of A intersection B is P of A into P of B, given that A and B are independent. So this is P of A complement into P of B complement into P of C complement. That will be P of A complement. So probability of A hitting the target 3 by 4, not hitting 1 by 4. B hitting the target 1 by 2, not hitting 1 by 2. P of C hitting the target 5 by 8, not hitting is 3 by 8. So this probability is going to be 3 by 64. Okay, with that we answer the third question, probability of the target being hit. Now target being hit means it's not necessary that all three of them hit the target. It's okay even if one of them hits the target, or even if two of them hit the target, it is fine, but the target needs to be hit, whether by 1 or by 2 or by 3, that does not make a difference. So you can say that probability of target being hit, right? Either the target will be hit or it will not be hit. So probability of the target being hit is the total probability, which is 1, minus the target not being hit. Okay, so we have this as 1 minus target not being hit is 3 by 64. So we have 1 minus 3 by 64, that is 61 by 64 as probability of the target being hit. And finally comes the D part, probability of the target being hit exactly by two of them. So that is something we need to calculate, just like we had calculated answer for our first question. First means the A part, okay. So for two of them to hit the target, it can be P of A intersection B intersection C complement, or the other possibility will be P of A intersection B complement intersection C, or P of A complement intersection B intersection C. Okay, so either AB will hit the target, C will not hit, or in the second case B will not hit and the other two will hit, or in the third case A and B will not hit and B and C will hit the target. Okay, like we have discussed, for independent events, intersection will be as good as multiplication. So this is P of A into B into C complement, that will be 3 by 4, 1 by 2, C complement, okay, so 3 upon 8, plus P of A, B complement and C, so that will be 3 by 4, 1 by 2 and 5 by 8. And the last one is A complement, B and C. A complement means 1 by 4, B and C are given, that's 1 by 2 and 5 upon 8. So let's multiply all of them. This will be 9, this will be 15, 9 and 15 make it 24, 24 and 5 make it 29. So we have 29 upon 64 as the answer for the D part. Okay, that's how easily you can answer all these questions. With that, we go ahead with our sixth question. The probability that a student X solves a problem in dynamics is 2 by 5, and the probability that a student Y solves the same problem is 1 by 4. So that's one probability, that's the other probability. Probability that the problem is not solved, so that's P of X complement intersection Y complement. Because they are solving it independently, we say that this will be P of X complement into P of Y complement, because intersection is multiplication for independent events. P of X complement, student solving the problem 2 by 5, so not solving is 1 minus 2 by 5, 3 by 5, into problem solving 1 by 4, so not solving 1 minus 1 by 4, which is 3 by 4. This gives you 9 by 20. What is the probability that the problem is solved? See, either the problem will be solved or it will not be solved. So the total probability will be 1, and we will say that probability of not solved, probability of solved is the total probability 1 minus probability of not solved. So that will be 1 minus 9 by 20, which is equal to 11 by 20. Okay, going ahead with the third one, the problem is solved by exactly one of them. So it's like x will solve and y will not solve. So P of x intersection y complement, or probability of x not solving and y solving. So x complement intersection y. So multiply the probabilities now. So probability of x solving is 2 by 5, y complement 3 by 4, plus P of x complement, that will be 3 by 5, and P of y, that will be 1 by 4. Okay, so if we just evaluate these numbers, the denominator will be 20 and the numerator is 6 plus 3, which is 9. So this will be equal to 9 upon 20. And is that right? Let me just verify that. So it's 6 and 9. Yeah, 9 upon 20 is the right answer for that third part. Okay, so here's the multiplication concept that I was talking about. For all those who know this concept, you can go ahead with the questions. For all those who don't know, here's the entire discussion. See, we said that P of A given B, the formula that we had learned was P of A intersection B upon P of B. Now, if A and B are independent events, the occurrence of B does not affect the probability of A. So whether event B is occurring or it is not occurring, the probability of A will remain whatever it is. So we will say that for independent events, probability of A given B will be P of A only, because whether B is occurring or not occurring, probability of A does not get affected. So P of A given B will be P of A only. But P of A given B, we were writing it as P of A intersection B upon P of B. So we take that P of B on the right and we say that P of A intersection B will be equal to P of A into P of B. And yeah, that's the discussion about independent events. That for independent events, the intersection can be written as multiplication of the two events. Now keep in mind, independent events doesn't mean that there is no intersection. Okay, there can be intersection between two events and yet they can be independent of each other. Independent events and the intersection of two events does not have anything to do with each other. Okay, so don't mix up those two concepts. It's a common thing which students get confused with, but now that I have discussed it, you should not get confused with that particular thing. Let's continue with the seventh question. So here it says that a person is speaking truth in 80% of the cases. Okay, not a person. A speaks truth. A is the person himself. So A speaks truth in 80% of the cases and B is speaking the truth only in 60% of the cases. Find the probability that they are going to contradict each other in a given incident. So if they are contradicting each other, then either A is lying and B is telling the truth, or A is telling the truth and B is lying. So we will say P of A intersection B complement. A tells the truth, B lies. Or the other possibility is P of A lying and B telling the truth. So this will be, if they are narrating an incident independently, the intersection will be multiplication of the two events. So I'll not write that separately. I'll put in straight away the values. P of A into P of B complement. P of A is 80%, so let's write it as 0.8 multiplied by P of B complement. B speaks the truth 60% of the times, so B will lie. The possibility for that is 40%, so we will write probability as 0.4 plus similarly P of A complement. A speaks truth 80% of the cases, so A complement will be 20%, that is 0.2, and P of B, that will be 60% because, okay, 0.6 because 60% of the cases B is speaking the truth. So we have 0.8 into 0.4, which is 0.32, plus 0.2 into 0.6, which is 0.12, and the final answer for that seventh question is 0.44. That's the final required probability. Going ahead with question number 8. 200 patients who either have eye surgery or throat surgery were asked whether they were satisfied or unsatisfied regarding the results of their surgery. So the following table summarizes their response. Okay, so throat surgery, 70 of them were satisfied, 25 of them were unsatisfied. Total there were 95 people with the throat surgery. For the eye surgery, there were 90 people who were satisfied, 15 people were unsatisfied, and total there were 105 surgeries for total there were 105 eye surgeries. So total number of surgeries were 200. Now out of that 200, if you check, the total number of satisfied people are 160 and total number of unsatisfied people are 40. If one person from the 200 patients is selected at random, determine the probability that the person was satisfied given that he had a throat surgery. Okay, so these are the typical conditional probability problems. So we have to find probability that the person was satisfied given that he had a throat surgery. This is going to be, you can say P of S intersection T upon P of T, or you can say N of S intersection T upon N of T. Either way will do. I will write N because here what we are given are the number of patients. Okay. So N of S intersection T, throat surgery and satisfied. So that is 70. And upon N of T is the number of people who had the throat surgery, and that's 95. So here the probability will be 70 upon 95. You can cancel off a 5 in the numerator and denominator to get 14 by 19 as the final answer. Go ahead with the B part. The B part says probability that the person was unsatisfied. Okay. So U, or you can even call it S complement, whatever you want to term it, P of S complement, given that the person had an eye surgery. Okay. So this is going to be N of S complement intersection eye surgery upon N of eye surgery people. Unsatisfied eye surgery people were 15. So the numerator here is 15 because we wanted the person to be unsatisfied and the one with an eye surgery, which is 15 only. And denominator is number of people having an eye surgery. So number of people who had an eye surgery is 105. Okay, so upon 105, that makes it 1 by 7 as your final answer for the B part. Try the C part as well. So for the C part, the person had a throat surgery given that the person was unsatisfied. Okay, so here they have reversed the problem. They are saying that you find the probability that the person had a throat surgery given that he was an unsatisfied person. So now it will be N of T intersection S complement divided by N of S complement. T intersection S complement means number of throat surgery people who are unsatisfied, which is 25, and N of S complement means the total number of unsatisfied people, which is 40. So here it's going to be 25 upon 40, which is equal to 5 upon 8. And yeah, that's how we are answering our third question. Typical conditional probability concepts. And yeah, I hope you are clear with that. Going ahead with the next one. Two dice are thrown together. Let A be the event of getting a 6 on the first die and B be the event of getting a 2 on the second die. Are A and B independent? So all you need to check is the independent event condition is getting satisfied or no. So probability of A, event of getting a 6 on the first die, that will be 1 by 6. Probability of the event B is what? Getting a 2 on the second die. So this is 1 by 6. Of course, I know most of you know the answer that of course they are independent. The outcome of the first die does not affect the outcome of the second die. So definitely they are independent. What is there to calculate in that? I know there's nothing to calculate in this, but this is just proving to you that mathematics does have a numerical solution to every kind of a concept that you are learning. It's just that we are not verifying whether the events are independent or no. What we are doing is like we are testing mathematics over here, whether mathematics is really going right or no. Think of it in that way, and accepting these kind of things will become a bit easier for you. And now let's go ahead with the sum. So we have P of A as 1 by 6, P of B as 1 by 6. Let's check what is P of A intersection B. A intersection B means you should get a 6 on the first die and a 2 on the second die. So that's only one possible outcome. And the total number of outcomes when you're throwing 2 dice, it's going to be 36. So P of A intersection B is 1 by 36. If you realize P of A intersection B is P of A into P of B. Because when you go for P of A into P of B, that will give you 1 by 36. And it is the same as P of A intersection B. And because P of A given P of A intersection B is equal to P of A into P of B, we say that the two events are independent because mathematically they are satisfying the condition of independent events. Okay, so yes, they are independent, and with that we go for answering our 10th question. The probability that a man who is 45 years old will be alive till he becomes 70 is 5 by 12. Okay, the probability that his wife who is 40 years old for now, she will be alive till 65 is 3 by 8. So they are talking about a time span of 25 years. The probability that a person will be alive for 25 years is 5 by 12 and his wife will be alive after 25 years is 3 upon 8. What is the probability that 25 years later the couple is going to be alive? Couple alive means husband also alive, wife also alive. So P of H intersection W, that will be P of H into P of W, which is 5 by 12 into 3 upon 8. And you can cancel off a 3 here and a 4 comes in the denominator. This will be 5 by 32. Okay, I am sure that many of you are thinking these are not really independent events. Why are you assuming them to be independent? The reason is, see, if a man contracts a disease, then there is a high possibility that because the man has contracted a disease, the woman also contracts the disease. So they are not really independent events, but just for the calculation purpose, we are assuming that they are independent events. Okay, so assuming that these two are independent events, here's the answer. But in reality, yes, if the two people are living together, there's always a possibility that one person becoming unhealthy affects the health of the other person also. And that is why these calculations in real life are not really that accurate. But okay, just to solve a sum, we are doing them. And we will do it to solve even our second question. Exactly one of them will be alive. So P of the man being alive intersection W complement, that is the woman not being alive, plus the man not being alive and the woman being alive. We need just one of them to be alive. So these are the only two cases. And P of M intersection W complement, it will be P of M into P of W complement. P of the man being alive 5 by 12 into P of the woman not being alive 5 by 8 plus P of M complement, that will be 7 by 12, that is man not being alive, P of W, P of woman being alive 3 by 8. So we have a 12 into 8 in the denominator, which is what, 96, and in the numerator we have 25 plus 21, which is 46. Okay, so you can cancel off that 2 in the numerator and denominator to get the final answer as 23 upon 48. And with that, we go ahead with part C. So with part C, you can say none of them being alive. So none of them being alive, there's just one case, P of W complement intersection M complement. And for independent events, we multiply the probabilities. So we have P of W complement, which is 3 upon 8, into P of M complement, which is 7 upon 12. And that cancels off a 3 here and here, giving you 4. So 7 by 32 is the answer for that C part. And D part says at least one of them being alive. So at least one of them being alive means either one can be alive or both of them can be alive. Well, if you realize, it's the exact complement of both of them being dead. So we can say that at least one of them will be alive or both of them will be dead. And that is why we can say that if this is the complement of the above event, the probability for this event will be 1 minus probability of the complement event, which is both of them being dead. So the required probability is 1 minus P of W complement intersection M complement, which we have got as 7 upon 32. So 1 minus 7 upon 32. The answer for this question will be 25 by 32. Yeah, that's how we are answering the 10th question. And with that, we go ahead with our 11th question. A box containing 10 red balls, 15 green balls. 2 balls are drawn in succession without replacement. What is the probability that the first one is red and the second one is green? So for the first ball, I think I'll go ahead with the method of blanks. So blank 1, blank 2, divided by blank 1, blank 2. So the first one to be a red ball, how many red balls do you have? 10. So the first blank can be filled in 10 ways because you can select a red ball in 10 ways. The second ball needs to be green. So in how many ways can you select a green ball? That's 15 ways. Now the number of, the total number of cases, the sample space. The first ball can be selected in, see, there are 10 red and 15 green balls. So any one out of the 25 balls can be selected as the first ball. So 25 possibilities for selecting the first ball. And after the first ball has been selected, see, it's without replacement, okay? So you're not putting that ball again back into the bag. So 25 possibilities for the first case, but once you have selected a ball, you put it aside. Now there are only 24 balls in the bag. So you can select any one out of the 24 balls as your second ball. So the second blank can be filled in 24 ways. Okay, we multiply the possibilities because they are connected by the word and. You are selecting a red and a green ball. You are selecting ball 1 and a ball 2. So because they are connected by the word and, we are multiplying the possibilities. So the final answer is 15 into 10 upon 25 into 24. Let's cancel all that we can. That's a 3 year, that's a 5 year. It's a 5 year, it's a 2 year. It's a 3 into 2, 6 and a 4 year. So the final answer is 1 upon 4 for that A part. And going ahead with that B part. One is red and the other is green. Now see, they are not talking about the sequence in this. They want one of them to be red and the other one to be green. So one red and one green. And how many ways can you select that? You can have 10C one ways for the red ball and 15C1 ways for the green ball, divided by the total number of drawing possibilities are going to be 52C2. Sorry, not 52. There are 25 balls, so 25C2. So if you try to evaluate this, this is going to be numerator as 10 into 15 divided by 25 into 24, the whole divided by 2 into 1, and that 2 into 1 goes up. So this becomes again the same thing. 5 goes once, 5 twos are, okay. This 5 again cancels off this 15 here. 2 into 3 will be 6, 4, and 2 and 4 get cancelled, giving you half. So the final answer for the second part is half. And you're wondering that what exactly is the difference between the first and the second one. See, the first one says you want red compulsorily as the first ball and green as the second ball. But the second one says that even if it is green first and red later, it is absolutely fine. So the total number of possibilities get doubled. Whatever were the possibilities in the first case were definitely there. But even if you reverse that selection, that is first green and then red, then also that possibility will be acceptable in the B part. And that is why the total number of possibilities for our event got doubled, which is why in the second case we got double the answer. In first case it was 1 by 4, in second case it was 1 by 2. Okay, so with that we go ahead with our 12th question. It says that a bag contains 3 yellow and 5 brown balls. Another bag contains 4 yellow and 6 brown balls. If one ball is drawn from each bag, what is the probability that both balls are of the same color? It's very clear that either both balls are going to be yellow intersection yellow. Let's call it Y1 and Y2. That is yellow from first and yellow from second, plus P of B1 intersection B2. That is brown from first and brown from the second. The selection of balls is going to be independent because whatever is the outcome from the first bag, that does not affect the outcome from the second bag. And because they are independent events, we will write those two intersections as multiplications. So this is P of Y1 into P of Y2. P of Y1, that is probability of getting a yellow ball from the first bag. That will be 3 yellow balls in the bag divided by 8 balls in total. P of Y2 similarly will be 4 upon 10 plus P of getting a brown ball from the first bag, that will be 5 upon 8, and P of, I'm sorry, not P of 5 upon 8, simply 5 upon 8 into P of B2 selecting a brown ball from the second bag, that will be 6 upon 10. The denominators are 80, the numerators are 12 and 30, 12 and 30 making it 42. So we have 42 upon 80, and you can cancel off a 2 in the numerator and denominator to get 21 upon 40 as the final answer for that A part. And the balls are of different colors. If you are thinking that we will go for Y1 intersection B2 plus Y2 intersection B1, you are absolutely correct, but there is a shorter method here. See, the total probability will be what? The total probability will be the probability of selecting balls of the same color or selecting balls of different colors. If probability of selecting balls of the same color is 21 by 40, then having balls of different colors, that will be total probability minus this case, that is 1 minus 21 upon 40, which will be 19 upon 40. Okay. Now because we had calculated the first part, we can calculate this very easily. But in case if your exams tell you to calculate only the second part, then you have to go by the longer method. The longer method, I'll just write it down over here. It was P of Y1 intersection B2, that is yellow from first and brown from the second bag, plus P of Y2 intersection B1, Y1 intersection B2, yellow from first and brown from the second bag. Okay. So you can evaluate this just like you have evaluated the A part and reach the final answer, which is 19 upon 40. But like I said, because there was a shorter method here, we have opted to go for the shorter method and reach the final answer in very few steps. Moving on with number 13. An urn contains 4 black and 5 white balls and 6 red balls. 2 balls are drawn one after the other without replacement. What is the probability that at least one of them is a black? Okay, so let's calculate this in the reverse way. That is, we will say 1 minus probability of no ball being a black ball. Okay, so we want no black. So 1 minus probability of no black. How many balls are we drawing? We are drawing 2 balls. So no black means probability of both balls being either red or white. Okay, so this is going to be equal to 1 minus, in how many ways can you select a red ball or a white ball? See, there are 11 balls total which are white, which are either white or red. Okay, so 5 white and 6 red balls, that is making it a total of 11 balls, and you can select any 2 out of these 11 balls for the required event. Okay, so that can be done in 11 C2 ways, divided by the total number of selections when you're drawing 2 balls from a bag which is containing 4, 5 and 6 black, white and red balls. So total number of balls are what? They are 15, and when you're selecting 2 out of 15 balls, that can be done in 15 C2 ways. So this will be 1 minus 11 C2 is 11 into 10 upon 2 into 1, but in the denominator you again have 15 into 14 upon 2 into 1. So that 2 into 1 gets cancelled, and we are left with 1 minus 11 into 10 upon 15 into 14. You can cancel off 5 here and a 5 here, that gives you 3, and the remaining 2 can be cancelled off with this 14 here. So that gives you 1 minus 11 upon 21, that is 10 upon 21 as the final answer for the 13th question. Let's go ahead with number 14. 3 fair coins are tossed. What is the probability of getting 3 heads given that at least 2 coins are showing heads? Now you need to understand this question very carefully, okay? It's not that you are tossing a coin, you are getting 2 heads in the first 2 tosses, and then they are asking you the probability of getting a head in the third toss. That's not the question. The question is this: 3 coins have been tossed, and how many possible outcomes can you have? With 3 coins being tossed, there are 8 outcomes which you can have: TTT, TTH, THT, HTT. Then there is THH, then there is HTH, then there is HHT, and finally there is HHH. These are 8 possible outcomes, okay? So any one out of these 8 outcomes has already come, and they are revealing, let us say they are disclosing any 2 outcomes out of the 3 outcomes that you have already had. Outcomes means these are 8 possible outcomes, but from the result that you have already got, maybe you have got this result. So from that result, you are being told that at least 2 heads are definitely there. Now what is the probability that there are 3 heads? Okay, so we are trying to find probability of having 3 heads given that we already have at least 2 heads. Okay, this will be P of 3 intersection 2, that is probability of getting 3 heads intersection with probability of getting at least 2 heads divided by probability of getting at least 2 heads. So probability of getting 3 heads means it is only this. Probability of getting at least 2 heads, that is all these cases here, their intersection is only 1, and that is why the numerator is going to be only 1. You can write it as n of 3 intersection 2 to be precise, and n of 2 in the denominator. So n of 3 intersection 2, we just saw it is equal to only and only 1 divided by n of at least 2 heads. At least 2 heads does not mean only this event and this event, because like I said, it's not first 2 coins getting tossed and then you're tossing the coin again only to check the last outcome, but the coins have been tossed. You know that there are at least 2 heads in your outcome. What is the probability that the third one is also a head? So we need to count even these 2, that is this and this, as a part of our sample space. Okay, so n of 2 is going to have 4 possible outcomes, and that is why n of 2 will be written as 4. So the final probability is going to be 1 by 4, and yeah, that's how we are answering the 14th question. Going ahead with the 15th one. 2 cards are drawn one after the other from a pack of 52 cards without replacement. What is the probability that both the cards are face cards? Okay, so how many face cards do you have? You have what, 3 face cards in one suit, and you have a total of 4 suits. So you have 3 into 4, which is 12 face cards. Any 2 out of the 12 face cards can be selected in 12C2 ways, and you're selecting 2 cards at random from 52 cards without replacement. You can do that in 52C2 ways. So the answer for that 15th question is 12 into 11. I know there's upon 2 into 1, but that upon 2 into 1 gets cancelled with the 2 into 1 in the denominator of this. So the denominator is 52 into 51. Upon 2 into 1 got cancelled with 2 into 1 of the numerator. So this is going to give you 2 into 6, sorry, not 2, 4 into 3 and 4 into 13, 3 into 1, 3 into 17. So we have 11 upon 13 into 17. That would be what? 169 and 52. So 171 and 52, making it 221. Yeah, that's the answer for your 15th question. Going ahead with the 16th one. Let's go ahead with question number 16. It says that bag A contains 3 red and 2 white balls, and bag B contains 2 red and 5 white balls. A bag is selected at random and a ball is drawn and put into the other bag. And then a ball is drawn from that bag. Find the probability that both the balls are of the same color. Okay, so understand that question properly. It's a very easy question. It says that you need both the balls to be of the same color. So let us say we are selecting the first bag. So probability of bag 1 to be selected, intersection from the bag 1, let us say you are selecting a red ball. Now with that, from the second bag also you have to select a red ball only. So intersection R2. Or you can have probability of bag 1 getting selected and a white ball coming out of it. But in this case, from the second bag also you will need a white ball only, because both the balls have to be of the same color. Or you can now select your bag 2 and have a red ball coming out of it, that is intersection R2. And if you are getting R2 from the bag 2, I mean a red ball from the bag 2, then you need a red ball from the bag 1. So that event will be R1. Plus you can select the bag 2 and get a white ball out of it. But if you are taking a white ball from the bag 2, then you need to have a white ball from the bag 1 as well, that is P of W1. Now these are numbers that you need to calculate. Assuming that these are all independent events, we will simply multiply their probabilities, and that simply can be done in this manner. So to evaluate those numbers, we have P of 1, which is 1 by 2, into, check this, R1. So a red ball coming out of the first bag, that probability will be 3 by 5 multiplied by, we have P of R2. Now that you have taken a red ball from here and you have put it in the second bag, there are 3 red and 5 white balls. So now the probability of getting a red ball from the second bag, that will be 3 upon 8. So into we have 3 upon 8 plus, go for evaluating the next term exactly in the same way. So P of 1 half P of W1. So that will be 2 by 5. So half into 2 by 5. And finally W2. You have taken a white ball from here, that is 2 by 5, the probability of which, the probability for that was 2 by 5. You're putting it in the second bag, which now has 6 white balls and 2 red balls. Now to get a white ball, the probability is going to be 6 upon 8. So into we have 6 upon 8 plus we have, for the second bag, the probability will be half. From that, you're selecting a red ball. So the probability for that will be 2 by 7 and you're putting it in the first bag. And now from the first bag, the probability of selecting a red ball will be 4 out of 6. So 4 upon 6. So this was 2 upon 7 and 4 upon 6. Plus half into, half because it's the second bag getting selected from which you're taking out a white ball. And the probability for it will be 5 by 7. And you're putting it in the first bag. So the first bag has 3 red and 3 white balls. Probability of getting a white ball now is going to be 3 upon 6, which is 1 upon 2. We will write it as 3 upon 6. So 5 by 7 and 3 upon 6. Let's calculate these numbers. So we have 9 upon 80 and 12 upon 80. 9 and 12 make it 21 upon 80. Plus we have 8 upon 84 plus 15 upon 84. So 8 and 15 making it 23 upon 84. Yeah, so I think the best would be cross multiply, but we should ideally take their LCM. Their LCM, that should be okay. I think best is we cross multiply because that's going to be a quicker thing for me. So it's 21 into 84 plus 23 into 80, the whole divided by 80 into 84. You can pull out a 4 common from the two terms. So you are going to have 21 into, this is going to become 21 plus 23 into 20, the whole thing divided by 20 into 84. Is there anything else we can do? No. So 84 into 20 will make it 1680 in the denominator. In the numerator, this is going to be 441. Plus we have 460. So 400 and 400 making it 800, 900. So this is 901 upon 1680. So a little bit of calculation involved in that. But yeah, the sum was actually an easy one because conceptually everything was quite straightforward. So yeah, that's how we are answering our 16th question. And with that, we go for one last question, that is the 17th one. A bag containing 3 red and 5 white balls. 2 balls are drawn at random without replacement. Find the probability that both of them are white balls. So how many white balls do you have? 5 of them. The number of ways by which we can select 2 out of the 5 white balls is 5C2. divided by you're selecting 2 balls out of 8, which can be done in 8C2 ways. So total number of possible selections are 8C2, out of which 5C2 are favorable to us. So this will be 5 into 4 upon 2 into 1 divided by 8 into 7 upon 2 into 1. That 2 into 1 gets cancelled in the numerator and denominator, so I have not written it here. You can cancel off these two terms and the final probability is going to be 5 upon 14. So yeah, that's where we are done with discussing whatever I wanted to discuss in this video. I hope that the contents have been someplace somewhere helpful to you in your preparations. Thank you for watching.